you might be worried at this point, that's not a prime, that's a square number, all right? But then we keep looking, and we get the following values. Just stop somewhere. That's good. Okay. 233 becomes 1, 3 becomes 1, 1 becomes 389, 1 becomes 3, and so on. And you can actually test this for 10,000, 100,000 values. And it turns out that all that happens is ones switch to primes and primes switch to ones. And you have this initial square. And you can change the value. If you change it to, say, 97, then the first square that arises is 5 squared, which you get 25. So you always have this pattern where you have some square and then some switching. And so that was interesting because in Eric's original description, there's this property called transience where even if not everything is generated, that's generated as a prime, at the very least you have some trail that you can cut off, and after that, everything becomes prime. So this adheres to that nicely, and you've got this funny little property. What happens if I go more general? What happens if I go to x to the third? Turns out x to the third is exactly the same as x squared. In fact, every x to the n, x to the 100, x to 10,000, is the same. Why? This is probably the more problem for the sake of time, but look at the GCD and you'll figure it out. Case 3. This one's kind of weird as well. F of x, where you map x to x plus k. We're going to break this up into two cases. Let's call the initial value for, let's call this x0, whatever. If we have something that's less than x0, then you have two choices. Oh, by the way, in the spirit of experimental math, all these results have completely no rigorous basis and are just derived by staring at it. So proof is forthcoming. But all right, so basically, you get one of two possibilities if you're working with k less than x0. Either you get trivial or essentially trivial, or you get prime generating recurrence. If it's greater than or equal to x0, then you have some trace, and then it terminates. So that's very strange that it happens to work out this nicely. So I'm kind of scared to move on to bigger polynomials, but this sort of wraps up for that. So, all right. Let's see what we got. All right. So I just want to make note of one last problem, and I'm going to keep going with this and see how far it takes me. But just sort of one other problem I've been worrying about is, in some sense, these look like duals or conjugates or something, but it's not very clear at all how you transfer behavior. So I'll give you an example. Cloitre in his paper actually notes something else very strange. Also a conjecture, also a problem. If you tweak this slightly, so doing the LCM version, tweak this so that you have a1 equals 1, a to the n equals 2 times a to the n minus 1 plus LCM n a n minus 1. And then for your gn, do an over a n minus 1 minus 2. He notes, again without proof, and what checks out, verifies empirically, that this sequence generates primes and omits greater twin primes. By greater twin prime, I mean you take a pair and the bigger one will not show up. So 5 won't show up, 13 won't show up, etc. So this morning I thought, this is in honor of Zeilberger, so I proposed that we refer to a sequence that omits greater primes as a Rebecca sequence, because they're twins and the younger one is favored and the older one is passed over. So, open problem, is this in fact a Rebecca sequence? Now, I tried to find a way to transport this idea to the GCD case, but it doesn't seem to work. It seems to rely on this LCM property, and it's very frustrating. So Instead, what you do when you can't solve something, you go on the internet and you find someone else who tried to do it already, and lo and behold, Vladimir Shevelev, some of you are familiar with his output. He also proposes something. These people, they're not really interested in the experimental aspect of it, they just want to prove the twin prime conjecture, so so he proposes the following. This is due to Shevelev. And this is interesting, what he kind of proposed here, is he splits it by n even and odd. And in fact, you can actually reverse even and odd in that definition, and the same behavior supposedly arises. What behavior is that? Only the greater primes, twin primes, are generated. So this would be the Isaac sequence. So the question is there in fact some relationship between these two? This piecemeal looking thing with GCD, and then this other thing with the LCM. And actually, you can replace this 2 here, and you'll have, replace it with a 6, you'll have something that deals with the sexy primes. So there's a whole lot that I don't understand yet, and maybe someone else here will figure out, but let's see. Very good. Any interest? Okay, perfect. All right, I think we'll just stop there then. If there are any questions.
The online encyclopedia.
Yes, I've been there.
Some of this is
Old hat for you guys. He just has like 20 related sequences to this. I can't do a script for all of these.
Is your motivation to prove the fact that
No, I'm just interested in see, wouldn't it be nice to have some kind of, no. Sometimes not interesting. I just want to understand why. You know, like I imagine that there might be some way even to combine the GCD with the LCM somehow, but that doesn't even, nothing checks out so far. I just really like to have a more general understanding.
Yes. Yeah. Have you tried looking at this p-adically at all?
P-adic, that's Eric's.
Because you might be able to avoid some of the big numbers doing it that way.
Right. How do you mean?
Like Boyd's did stuff with the harmonic series.
Okay.
Checking when that vanishes lots of time.
Yeah, you'll avoid some big stuff, but then we'll have to look at that.
Any other questions?
if not, let's thank this again.
I just want to add one last word in honor of our honored guest, host, whatever. Sometimes you're married for a long time and you still love your spouse, but the passion has sort of died out. And I just want to thank Doron Zeilberger for giving me back the passion for mathematics.